Thank you very much. Welcome to today's class. I'm very happy that you are connecting with me in this unit, and it's very important. We have already dealt with other units in these other topics in this unit. We've already covered a unit on variability. And this is a subtopic that we are covering currently in this class on variability of sampling. I'm very glad that my other classes I've sent to you, and you are doing the necessary to catch up so that you become a scholar who is ready to carry out research. And now you are getting the nitty-gritties of carrying out research in the of nitty-gritties of carrying out research in the research vocation. Today, I'm going to deal with um, part of what we are dealing with, because we are dealing with finite and infinite populations when we are doing sampling. And today I'm dealing with the finite populations, and I'm looking at one particular thing, finite population correction factor, which is very important in the field of education and when you are doing sampling. Let us get or dive in it and see what it has, what this topic has for us. The finite population correction, commonly known as FPC, is a multiplier applied to the standard error of a sample statistic when sampling is done without replacement from a finite population. Its purpose is to correct for the overestimation of standard error that occurs when using formulas derived from infinite or very, very large populations. There are formulas that are used for this. For calculating FPC, and the formula is FPC, that is finite population correction factor, equals to, you'll allow me to take my pen so that we can be able to move together in this lesson. So FPC, that's finite population correction, equals to the root of the entire population, which is represented by n, is n, then the sample represented by lower n, all over the entire population, n minus 1. And as I've said, n represents, the capital N represents population size, and small n or lowercase n represents the sample size. Why is it necessary to use finite population correction? It is necessary because, one, infinite population assumptions, which uses the formula tilde, this letter that looks like A, and all over root n lowercase, that is the sample, assumes an infinite population, which inherently is overestimates sample error by ignoring the finite nature of all the real world populations. The second reason why it's necessary for us to do FPC, that's finite population correction, sampling without replacement from a finite population make each selected item unavailable for future draws. That's why we say that it's without replacement, which reduces the variability and makes the sample more representative than an infinite population model that will predict. Then there comes the correction. The finite population correction factor shrinks the calculated standard error to accurately reflect the increased precision you gain when your sample represents a significant fraction of the total population. When do we apply the FPC? When do we apply the finite population correction? A common rule of thumb is to apply FPC when the sample size is more than 5% of the population size. That is, when the sample population is greater than 0.05 multiplied by the entire population. And this is how we get it easily. You will be able to take the sample size and divide by the entire population, n over capital N, sample size over the population. When it's smaller than 5%, then we say that FPC, that's finite population correction, is very close to 1 and has negligible effect. So it is often omitted. We don't use it. We have the practical implication or how we go step by step on calculating the finite population correction. We have to calculate the original standard error that is from the infinite population. And this one is given by the formula appearing on our screen. That is standard error equals to standard deviation. This represents the standard deviation all over the root of the sample, which is represented by lowercase n. Then we also have to calculate the corrected standard error, which is for the finite population. So the standard error, which is corrected in this case, equals to this infinite standard error. We bring it down like what you're having on the screen there. Then we multiply it by FPC, which is finite population correction. And we said that finite population correction, this one, usually is calculated by population minus sample, and all this should be in the root. So root population minus sample all over population minus 1. Because the finite population correction factor is always less than 1 when a sample is greater than 1. The corrected standard error is always smaller. leading to a narrower confidence interval and more powerful hypothesis tests. Let's continue flipping our book so that we see some examples for calculating the finite population correction. One of the example, a simple example, not a complicated one. A researcher is estimating the average height of students in a school of 100%, a population of 100 students. It takes a sample of 20 students to participate in the research. How do we move or how do we calculate the finite population correction for this? The finite population correction is given by root population minus sample all over population minus 1. And this one will give us 100 minus 20 all over 100 minus 1, and all this one is in the root. This one will give us root 80 over 99. And when you do the calculation using this part, it will give you 0.899. So the finite population correction in this area or in this example is 0.899. If the sample standard deviation implied a standard error of 2 centimeters using the infinite formula, then the corrected standard error will be, you take the standard error given, multiply by the FPC. This one will give us 1.798 centimeters. How do we interpret this? We look at the original standard error, which is 2 centimeters, and we look at the corrected standard error after applying FPC to get 1.798. This means that by applying the FPC, we recognize that our sample of 20 students from a population of 100 provides a more precise estimate than a simple standard error formula would suggest. The corrected standard error is about 10% smaller, which will result in an narrower, more precise confidence interval for our estimate of the average height. This correction is necessary because our sample is larger relative to the population. When you take the population, the sample divided by the population, you get 20%, which is greater than 5%, which is the rule of thumb. Now, I want us to move a step further and see the key significance of applying the FPC in our research. The following reasons are very, very important to be considered when applying, or they are very important when applying the FPC. The first reason is that FPC reduces the standard error. FPC is used to correct or reduce the standard error of our sample statistics, and we use like the sample mean or the sample proportion. Second, the FPC improves precision. The FPC results in a narrow confidence interval for the population estimates. Number 3, it increases the statistical power. By applying FPC, one can increase the statistical power of a study and can also lead to a smaller required sample size for a given level of precision. Number 4, which is our last point, in this case, FPC, or finite population correction, accounts for sampling without replacement. When you sample without replacement for a small population, each item drawn affects the probability of drawing subsequent items. The FPC mathematically adjusts for these non-independence. I'll move on to look at the implication of FPC, finite population correction, for education planners and for education policymakers. How can they use finite population correction in their day-to-day work? And how do these affect their work? I'm going to give several examples in this lesson so that we can see how planners and policymakers in education can be able to use this FPC. Example number 1. I'm going to consider a person evaluating a curriculum in a large school district or in a county or in a country. Now, the key policy or the key goal here will be, maybe somebody is determining the average math score for the population of 6,000 high school students in a large metropolitan school district after implementing a new costly technology-driven curriculum. In this research assembles 600 students to be tested. When you look at the sample and the population, because we say the population is 6,000, but here the researcher is sampling only 600 students to take part in the study to be tested to see the effectiveness of this curriculum. We want to see the sampling fraction by taking the sample size over the entire population. The sample size, which is 600, over the entire population, which is 6,000, gives us a fraction of 0.1. When you multiply by 100 to give us a percentage, we find that this one is 10%. And this one is significantly greater than 0.05. Then we have to apply finite population correction. Suppose in this data, the research finds that the standard deviation was 100. Then we proceed in step 1 to calculate the uncorrected standard error by applying a formula. Standard error uncorrected equals to standard deviation over the root of the sample size. In this case, 100 is the standard deviation all over the root of 600, which is our sample. When you do the calculation, it gives us 4.08. Then we proceed to step 2 to calculate the finite population correction, FPC factor. And in this case, we are going to apply the formula for FPC, which is root the entire population minus the sample all over the entire population minus 1. In this case, our population was 6,000 and our sample was 600. So it's 6,000 minus 600 all over 6,000 minus 1. You get 5,400 all over 5,999. And it's in the root. When you calculate this part, you get 0.94876. Then you move to step 3 to calculate the adjusted standard error or the corrected standard error from the finite population. The corrected standard error is found by multiplying the uncorrected standard error by the finite population correction factor. In this case, the standard error for finite equals to standard error uncorrected times FPC, and in this case, it is 4.08 on page 11 in our book here. We get that value, it's there. Then on page 12 here, our value we calculated up here, it's here. We bring it here and we multiply them together. Then we get a standard error of the finite or the corrected one of 3.873. We move on and we look at the interpretation of this for policymakers or policy implementers. Before FPC, the initial analysis suggested that the sample mean had a standard error of 4.08. But after FPC, the corrected analysis accounting for the population larger than 10% sample fraction showed that the standard error is actually 3.87. Now, when you take 4.08 minus 3.87, you realize that you get a difference, and when you calculate the percentage of this difference, has some matters in policy. So we say that this increased precision from 4.08 to 3.87 results in a narrower confidence interval. For instance, a 95% confidence interval will be tighter, giving policymakers a more precise estimate of the true average in this maths course. This smaller standard error results in a narrower confidence, and this increased precision means the policymakers can be more confident that their sample average actually reflects the true district-wide impact. Of course, justifying the curriculum large cost with certainty. Ignoring the finite population correction will result in a less precise, overly cautious estimate. And this case, we've seen that when applying our finite population correction, it reduces the standard error. Let me bring another example for also planners and policy implementers. This example I'm drawing from auditing special education compliance. And it goes, a state agency wants to audit compliance documentation for all 850 special education students in a small rural region. And due to time constraints, the state agency randomly samples 150 files of the special education students. Then when you look at the sampling strategy, you look at the sample and the population. When you want to get the fraction to see whether we can apply the finite population correction, You take the sample over the population, you get 0.176. Multiplied by 100, you get 17.6%. Then, in this case, the finite population correction is mandatory. The data shows that the sample mean error is 4%, and the sample standard deviation is 1.5%. Then we proceed to calculate the FPC, finite population correction, by taking the root of 700 Where are we getting the 700 from? 850 minus 150 all over 849. Where are we getting 849 from? 800, which is the entire population minus 1. Then all of them under the root. So we calculate and we get our FPC. This time around is going to be 0.9080. Then we take the FPC and multiply with 1.5%, which is our standard deviation, all over the root of 150. We get our adjusted standard error is 0.10. And of course, if you have to calculate, you'll get that uncorrected one, and a corrected standard error will be 0.122. So in this case, policy implications for this: if the state uses the uncorrected standard error of 0.122%, the resulting confidence interval will be wider. But when we apply the FPC and obtain a narrower interval, the policy planners can more precisely estimate the true regional error rate. And this precision is critical, as we are seeing, which stands now at 0.112, 0.11, not at 0.12. Now, the state might, through the policy, determine whether the region needs mandatory intervention if the high compliance rate is confirmed, or just a minor administrative training if the estimate error is within the acceptable limits. The finite population correction factor prevents officials from overstating the uncertainty and potentially misdiagnosing a compliant issue. In summary, for education planning that deals with specific countable population, like a single district, grant recipients, or a graduating class, the finite population correction is a necessary adjustment. It guarantees that the standard error of the mean accurately reflects the increased precision gained from sampling a significant proportion of the limited population, leading to a more accurate estimate, tighter confidence intervals, and better informed policy decisions regarding resource allocation, accountability, and program evaluations. I have questions for us to consider, and at your own free time, please try to attempt these questions because they will give you practice and you will develop your prowess in using finite population correction factor. Question 1. I've grouped these questions into different categories, and question 1 deals with the district-wide survey. The Ministry of Education is rolling out a new literacy program and wants to evaluate its impact on reading comprehension. The program was implemented in all public schools in a specific district, which has a total population of 2,500 grade 5 students. The evaluation team draws a random sample of 500 students for standardized testing. Required: calculate the finite population correction factor for this survey. Second, if uncorrected standard error for the average test score is calculated to be 1.5 points, what is the correct finite population adjusted standard error? Final on this question. In one sentence, explain to a senior policymaker why this adjustment was necessary. Question 2, looking at the impact of teacher training program. TSC is assessing the effectiveness of a new mandatory professional development course for science teachers. There are 8,000 teachers certified high school science teachers in the region. TSC surveys 1,600 of them to measure their self-reported confidence in the teaching of the new curriculum standards. Required: what is the sampling fraction? Does it exceed the 5% threshold for using the finite population correction? Calculate the finite population factor. The initial analysis, ignoring the FPC, showed a standard error of 0.8 for the average confidence score. Recalculate the standard error using the FPC. Question 3. There is a large program that is to be evaluated, being implemented by the county government. A non-profit organization wants to estimate the average daily participation in a subsidized school lunch program across 200 school partners. They collected data from a random sample of 40 schools. From the sample, they calculate a mean daily participation of 300 schools with a standard deviation of 50 students. Calculate the standard error of the mean without the finite population correction. Calculate the finite population correction factor and then correct the standard error of the mean. Using the corrected standard error, construct a 95% confidence interval for the true average daily participation across all the 200 schools. How will this interval differ from one calculated without finite population correction? Another question dealing with cost-benefit analysis of tech integration. A policy analyst is evaluating a pilot program that provides tablets to students. The pilot includes a population of 1,000 students. The analyst chooses a random sample of 300 students and finds that the average improvement in digital literacy score is 15 points, with a sample standard deviation of 12 points. Required, determine the finite population correction factor. Second, calculate the 95% confidence interval for the true average improvement for all the students in the pilot using finite population correction factor. The program is considered cost-effective if the lower bound of the 95% confidence intervals is at least 12 points. Does the corrected confidence interval support the conclusion that the program is cost-effective? Will the conclusion have been the same without using the FPC? Question 5. On strategic sampling for national assessment. You are designing a national assessment, and the budget allows for 2 possible sampling strategies for the population of a population of 50,000 students. Plan A requires that you sample only 5,000 students. And Plan B requires that you sample only a smaller, more logistically manageable sample of 2,500 students. Calculate the FPC factor for both plans. Ignoring the cost and logistics, which plan provides a more precise estimate? Quantify your answer by calculating the relative size of the FPC factor for Plan A and compare it with Plan B. Beside the FPC, what other practical factors related to cost and data quality should influence the final decision? Question 6, and I think this is my last one. Interpreting a consultant report. A consultant report to your school district states, we surveyed 600 students out of 3,000 teachers. The margin of error for the overall job satisfaction score is positive negative 3%. The report appendix notes that the standard error was calculated without applying a finite population correction, FPC, required from you. Was the consultant method technically correct? Justify your answer with a calculation. Recalculating the margin of error by first calculating the FPC factor and applying it. Assume that the positive negative 3% was derived from 95 confidence level. As the head of policy unit, write a brief memo of 2 to 3 sentences. Explain the implication of this error on the school board. You can pause this video to go through the question again, write them, and try to calculate or try to do them as you've been instructed. Thank you very much for having me and having you in this lesson today. Let's meet next time.